Okay, let's start. Welcome everyone to senseFly Academy. Today I have with me Adam Zilka from the US team and Michael Blake from the support team here in Switzerland. This part will be covered by Michael.
Hi everyone, my name is Michael and I'm part of senseFly CSS, our customer support and satisfaction. Today I want to talk about the use of emotion with PPK and RTK for personal and national GNSS receivers and the configuration between both. So the advantages of RTK and PPK. From relative accuracy to absolute accuracy without the need of ground control points. So traditionally for photogrammetry, all geographical corrections would have to be done from the use of ground control points on the ground, which would be picked up by a surveyor using either PPK or RTK, correction from a base station or rover, or using a VRS. The advantage of this using the RTK with our EBs is to reduce the amount of time on the ground and to eliminate the need for a surveyor to put down ground control points. So when to use RTK or PPK? Generally, RTK is always the first option to use. It will provide the best accuracy possible on the day of flight. So always start with RTK or VRS for that matter. PPK is the kind of second option for this. If RTK results are not good enough, if the link lost during the flight, for equipment for the RTK is not available, internet connection goes down, or your base station, there's a faulted base station, or your software freezes in your base station, it acts as a backup for that. So the multiple ways of achieving high accuracy. Standalone with GCPs. It's obviously, as I said, it's time consuming. It requires specialist equipment, a surveyor on the ground, and RTK and VRS. Multiple services are out there at the moment for VRS. So here in Switzerland, we have Sysbus. In the UK and parts of Europe, there's Trimble VRS now. In the US, there's USGS. And all you need for that is a phone with 3G or 4G, and that's it. So you can connect your phone to your laptop, use the GNSS receiver on the EB to establish your VRS, and you're good to go. RTK with a base station. So there's many different types of base station, which I'll concentrate on today. Obviously, the well-known makes of base station is Topcon, Leica, and Trimble. From that, then you can also post-process with most of those base stations using the observation file converted to Rines, and I'll address that also. PPK and VRS, same as RTK and VRS, both post-processing, so no stress on site. PPK base station from a cores. As I said, there's many new cores and VRS stations, especially on Europe and the States. VRS independent. So usually you'd want to keep your cores network close to your site to within 30 kilometers. After 30 kilometers, your correction and your accuracy starts to decline. So within 10, 20, 30 kilometers of your survey site, it's good. RTK real-time kinemetrics. So the three options with EB, as I said already, is standalone using GCPs. Our virtual reference station using a core-based network through the internet or through the L-band satellite with the new Trimble TRX now to get correction. Local base station on a known or unknown point. This is using your own personal base station in collaboration with emotion to correct your EB's GNSS receiver in real time. So we'll address VRS now quickly. You will need a subscription to a VRS network. This will give you an mtrip password, and you can add this to emotion. The ideal situation for this is that if you do not have a base station, you can still correct your EB's geotags through a VRS network. using the EB's GNSS receiver to get your first station, VRS station point on the ground. Next, we'll talk about RTK specifics and a base station on an unknown point. So for your base station, you need to have your base station set up in a base mode. You need to transmit in RTCM 2 or 3. It will need to read GPS and GLONASS signal. The baud rate is usually set to 1152.00. Ensure that you have the correct cables or Bluetooth set up. Some base stations are supplied with USB for data transfer. Sometimes this can be the wrong connection. You need to use a serial cable for this, usually a 9-pin limo connection. And also it needs to be logged in WGS84. In this situation, we are using our base station on an unknown point, so uncorrected point. So as you can see here, we're using a TOC1 Hyper RS. We've selected on an unknown point, and we've opened the drone-based data stream. So in this situation, our station, our GNSS receiver, is connected to a laptop, and we're receiving data from the RTCM port. So the longitude, latitude, ellipsoid height corrections, as you can see now, are uncorrected. So they're within 2 to 3 meters on the X and Y axis, and to within 4 or 5 meters on the Z axis. As you can see here, our format is we're using the RTCM3. We can see our GPS, our GLONASS, our antenna type, which I'll reflect on later on, and our approximate position of our base station uncorrected. Later on, we can then post-process the position of our base station in Flight Data Manager. So as you can see, for this example, we've actually corrected our base station on a known point. So from here, we've connected to our Hyper SR again. We've selected a reference point. We've added the known position of a reference point, which we could have either known before the flight, or we've got on the day using a VRS setup with our GNSS receiver to log for a few minutes the exact position of that point. Then in eMotion, we've added our base station. We've selected on a known reference point. We've selected that reference point. We've added already. Also, we can adjust the antenna height and offset that. So we select ground point in the height reference, and we give the known height of our GNSS receiver above the known point. And as a result, we can see that when opening the base downstream, that our position has been corrected. And before flight, as you can see in VRS or in RTK, where our format is in RTCM3, our GPS is good, our GLONASS is good. And also on the right side of the screen, we can see our EB. So we're reading 15 satellites, and our accuracy is 7 mil before flight. And our RTK is also fixed. So the EB geotagging. As EB RTK is flying in its designated mission, it enters its internal GPS receiver, logs the drone's position each time an image is captured by the onboard camera and transmits to eMotion. It also logs and transmits the accuracy of each of these geotags. So without RTK or in standalone mode, this represents the relative accuracy of the log coordinates at the moment the images were captured. This typically can be between 2.5 to 3.5 meters horizontally in the X and Y, or and 5 to 6 meters vertically on the Z axis. So to georeference, in this situation, we will have to use our ground control points or checkpoints. With RTK corrections, it represents the corrected position of the accuracy in the XYZ axis. The RTK correction is sent by the ground modem beside you on the ground, beside your laptop, to the EB in flight. The detectable accuracy of this RTK correction is between 10 to 20 millimeters horizontally and 20 to 30 millimeters vertically on the Z axis. Currently, we are expanding the capability range of our GNSS receivers in eMotion. There are some key features which need to be included on your GNSS receiver for it to configure with eMotion correctly. For emotion tree, to configure successfully with your GNSS receiver, does your GNSS receiver have real-time kinemetrics as a feature? So it needs to have RTK built in. Does it have a fixed solution type or a static observation type? So it needs to be in a static mode or base mode, as some manufacturers have. Can it output in RTCM2 or RTCM3? RTCM3 would be ideal in most situations. Can the base connect to your computer via serial cable or Bluetooth? Does your base collect GPS, GLONASS, L1 and L2 satellites? And also vital to get correction, does your base log in 1 Hertz or 1 observation per second? Now I'm going to focus on the message type, which needs to be sent via your GNSS receiver. There are several types of messages that can be sent through RTCM version 2 or 3. As you can see below, we have the different messages types. So 1004 is the extended L1 and L2 GPS RTK observations. These are vital to get correction. 1006 is a stationary RTK reference. 10112 is the extended L1, L2 for GLONASS, similar to 004 for GPS. Also vital is 1008, antenna serial number and antenna description. And lastly, 1033, receiver antenna descriptors. Usually the amount of data sent, if the necessary messages are selected, should be approximate 0.5 kilobytes per second. So, post-processing kinemetrics in emotion. We'll focus on a base over known point and unknown point again. For post-processing, with a Rines file from a local or national cores base network, the base station must be logging in Rines 2 or Rines 3. Usually we use Rines 2.11. Many base station observation files will be written in the specific format of the maker model of their GNSS receiver, e.g. Strimble would be the TMB file, Topcon would be the TPS file, Leica the DBX file, etc. A third-party convert to Rines software will need to be used to convert the raw GNSS or raw GPS observations file to a usable Rines file for emotion. For the Rines file to post-process successfully with emotion tree, it will need to contain the L1, L2 bands for GPS and GLONASS, together with the D1 and D2 Doppler shift, logging at 1 second intervals or 1 observation per second, 1 Hertz. So this should translate into L1, L2, G1, G2 for GLONASS, D1, D2 for a Doppler shift at 1 Hertz. Also necessary for observation file for successful PPK correction is the pseudo reg, which is the P1, P2 code, or both the C1, C2. In its entirety, the receiver bands required is L1, L2, G1, G2, D1, D2, P1, P2, or both C1, C2. Some GNSS receivers also provide the L band correction satellite and the S band. However, these are not necessary for PPK correction. The antenna type is also a necessity for both RTK and PPK. This gives the L1, L2 offset relative to the satellite's elevation at the time of observation. If your GNSS receiver does not transmit the antenna type through the RTCM, they will not be compatible with emotion for RTK or PPK process. Below is an example of a good Rines file. As you can see here, we have the L1, L2, and L5, C1, P1, P2, C2, C5, D5, D2, S1, S2, and S5. And the intervals is 1 second, so that's 1 observation per second. So in Flight Data Manager, RTK VRS are base station on a known point. The geotags are the absolute accuracy. So this is the best situation possible we are flying either on VRS or with a base station corrected, and every geotag is being corrected in real time. So no more post-processing needed of the base station or correction of the base station. So our base station over an unknown point. So we either need to correct the base station using a known coordinate system or known coordinates of the ground, of our point on the ground, or we need to post-process the base station Rines with a cores network Rines to get the position of our base station to process our geotags. So as you can see here, we've selected RTK PPK. We have our longitude, our latitude, our lift slot height. We have our antenna height at 2 meters. So we need to post-process that, or we need to correct that using our known position. On the right side, you can see we're using our Rines file from our cores observation to correct our personal base station on site, of which we don't know the position of, which we've used to geotag our EB's images. So in this situation, like before, we've seen standalone mode. We would need to either use our ground control points, which we've laid out to correct this flight, or we'd have to use our PPK or our cores network base station Rines to correct these images. Of course, again, we need a RTK or PPK license to do so. So for this situation, we can see we're using our PPK post-processing for the imagery. So we've included our cores network observation file, which then will give us the longitude, latitude, and lift slot height of that known base station and the reference height. From that, then we can correct our EB imagery. For example, here in Switzerland, we can select our Rines file using the Swiss Post website. So from here, we can select our base station on the cores network, obviously within 30 kilometers of our flight, our GPS occupation time, and interval is 1 second. So on the right side, we can see our observation period, the date of which we flew, the start time, 1 p.m. The duration was 45 minutes, which it coordinates with our EB's flight time at the time. Intervals are always going to be 1 second. So after collecting the Rines file and inputting it into Motion, we can see we have our observation file, our navigation, and our corex. From there, we can see our longitude, our latitude, and our lift slot height of the base station. And next, to process the imagery or the geotags. From here, then we can see the geotags and post-process. We've had originally standalone, 100%, 5.7 meters accuracy. In post-processing, then we can see we brought that down to 41 millimeters for all the geotags.
Thank you very much, Michael, for all these details about the base stations. Bye, everyone. Thank you for joining.